Hello and welcome, brothers. It's great to have you here for this explainer on the absolutely critical ultra-pure water mixed bed regeneration process. I am an operations expert for UPW Systems, and today we're going to completely master the exact standard operating procedure for regenerating our ion exchange resin. This is literally the absolute foundation of our final polishing stage before the water reaches the point of use. So let's dive right in. Here is our exact roadmap for today. We're going to run through the mixed bed system overview, exactly when to regenerate that resin, some common operational mistakes to avoid, the step-by-step regeneration procedure, our critical safety protocols, and finally, a few essential key takeaways. Section 1, Mixed Bed System Overview, the final polishing stage. Picture our overall mixed bed skid sitting right there in the clean room. Under that bright lighting, you'll see those neatly arranged white utility pipes and the modern dark blue control cabinets, right? Well, this skid is our final line of defense. It acts as the ultimate polishing stage to remove all remaining ions after the reverse osmosis and EDI stages, right before the water hits the point of use. Now, notice the cross-section of the column here. I really want you brothers to visualize what's actually happening inside that pressure vessel. We essentially have two types of ion exchange resins hanging out together. Down at the bottom, we have the heavier cation resin in the H+ form, which usually has this dark amber, kind of brownish color. And sitting right above that is the lighter anion resin in the OH- form, which is typically a transparent, milky white. When water flows through, it's like a giant chemical puzzle. The cation resin exchanges ions like sodium and calcium for H+, while the anion resin exchanges chloride and silica for OH-. These H+ and OH- ions then combine to create pure H2O, giving us that massive, beautiful resistivity of over 18.2 megaohm centimeters. Section 2. When to regenerate resin. Diagnosing the problem. So, over time, the functional sites on these resins become completely saturated. They literally just can't take any more. Here are the exact warning signs you need to look out for, so you never second-guess when regeneration is necessary. First up, keep an eye out for your output resistivity dropping below the design spec, especially if it's showing a steady downward trend. Second, look at your silica content. If that spikes above 0.5 parts per billion, you definitely have a problem. Third, watch for any abnormal increase in total organic carbon, or TOC, because that signals organic fouling or saturation. And finally, an increasing differential pressure across the column, that means the bed is getting compacted or clogged up. If you're in the control room, you should be constantly monitoring your SCADA screens. Picture the dashboard showing a downward trend in resistivity over the past 7 days, maybe accompanied by a blinking yellow warning light. When you see those silica high or differential pressure high alerts populate on your alarm list, trust your system, guys. It is officially time to regenerate. Section 3. Common operational mistakes. Risks to avoid. Now, before we get our hands dirty, we really need to talk about what not to do. Lacking caution here can cause severe cross-contamination, or honestly ruin the entire UPW loop. So pay close attention, brothers. Some of the absolute biggest mistakes include failing to achieve a clean separation during the backwash. This directly leads to acid and base cross-contamination. Another fatal error is regenerating at the wrong water temperatures. You absolutely must stay within that 20 to 25 degrees Celsius sweet spot. Actually, if you go outside that range, you will severely impact the ion exchange reaction kinetics. Also, never use incorrect chemical concentrations. Never skip your mixing or final rinse steps. And please, brothers, never ever fail to verify your final water quality before opening those valves back to the main loop. Section 4. Step-by-step regeneration. The exact procedure. Okay, go ahead and grab your P&ID diagrams. We are moving into the strict sequential breakdown of the operation, starting with the preparation phase. These initial steps, so preparation, backwash, and drain down, they set the absolute foundation for a successful chemical exchange later on. Step 0 is preparation and PPE. You absolutely cannot rush this. Put on your full chemical protective gear. I'm talking thick rubber gloves, goggles, rubber boots, and a full chemical suit. Check your hydrochloric acid and caustic soda tanks to make sure they are full and at the correct concentration. You must verify your flow paths against the P&ID, notify the central control room that you are isolating the column, and properly apply your lockout, tagout procedures. The whole shebang. Moving into our first mechanical action. Step 1, the backwash. We flow clean water upwards from the bottom of the column for 10 to 15 minutes. The goal here is to expand the bed by 50 to 75%. You need to carefully watch the sight glass here to ensure the lighter, white anion resins float to the top and the heavier amber cation resins settle at the bottom. You want a perfectly clear separation line. Actually, scratch that. You want a perfectly clean separation line without flowing so hard that you literally wash your expensive resin right out the overflow. Step 2 is the drain down. Once separated, you slowly lower the water level until it sits exactly 5 to 10 centimeters above the top of the settled anion bed. Why? Well, leaving just this tiny buffer of water prevents the incoming acid and base chemicals from becoming way too diluted during contact, while still protecting the resin itself. Now we transition into steps 3, 4, and 5. This is the chemical dosing and rinsing phase, and it's the absolute core of restoring our ion exchange capacity. Step 3 is regeneration. We use a counter-current method here. The yellow acid line feeds 4 to 5% hydrochloric acid from the bottom up through the cation resin. Meanwhile, the purple caustic line feeds 4% sodium hydroxide from the top down through the anion resin. Running these chemicals in opposite directions ensures they constantly contact the most exhausted resin first, which really maximizes the exchange driving force. This dosing needs to run steadily for 30 to 60 solid minutes. Step 4 is the displacement or slow rinse. Once the dosing pumps stop, do not just open the floodgates. We will use a slow deionized water flow here to gently push the remaining chemicals out of the resin beads and right into the neutralization pit. This slow displacement prevents shocking the system with a sudden drop or spike in pH. Step 5 is the fast rinse. Now we increase the DI water flow to thoroughly wash out any remaining traces of chemical. Grab a handheld meter and watch the conductivity drop steadily on your sensors until we hit our safe thresholds. That means a pH between 5 and 7 and a conductivity strictly under 10 microsiemens per centimeter. Step 6 is the mixed air and water stage. We need to turn those two distinct layers back into a single, beautifully uniform mixed bed. We push clean instrument air from the bottom at 1.5 to 2.5 bar, along with a trickle of DI water. Brothers, keeping air pressure strictly low is vital here. If the pressure is too high, you will literally fracture the resin beads, totally destroying their lifespan and causing ion leakage down the road. No way we want that. Step 7 is the final rinse. We flush the newly mixed bed with operational flow rates. You are going to watch your SCADA screens like a hawk here. Only when TOC, silica, and dissolved oxygen are completely stable and you verify a perfect 18.2 megohm centimeter resistivity for at least 30 solid minutes can you even consider the job done. Once that beautiful green, ready-to-service light turns on, you can slowly open the inlet and outlet valves back to the main distribution loop. Section 5. Critical Safety Protocols. Protecting the team. Technical accuracy means absolutely nothing without safety. When handling these highly corrosive acids and bases, a tiny slip can cause severe, life-altering injury. Remember these non-negotiables, guys. Wear your full PPE. Visually locate your emergency eye wash and safety shower before you turn a single valve. Ensure absolutely all waste is routed securely to the neutralization pit for pH balancing before environmental discharge. Strictly follow your lockout-tagout procedures. Never stand directly facing a flange or hose connection in case of a blowout. And finally, always use the buddy system. Never, ever work at chemical regeneration alone, period. Section 6. Essential key takeaways. Final thoughts. Brothers, the quality of your regeneration directly dictates the quality of the ultra-pure water for the entire plant. Skipping the backwash separation or the air mixing just ruins the column's efficiency. But above all else, be patient, especially during that final rinse. If you have any doubts at all about the water quality metrics, just keep rinsing. An extra 30 minutes of caution saves the entire distribution pipeline from a catastrophic contamination disaster. So I'll leave you with this to think about. Is rushing the process ever worth risking a multi-million-dollar cleanroom shutdown? Trust your instruments, protect the system, and take real pride in the absolutely pure water you produce.